In the last segment, we looked at different definitions and we talked about what it really means to be soluble and insoluble, and that what we really see when we see something that's aqueous is that we really see something that looks like water. It might be blue water or red water or a colored water, but it's still going to look like water. Okay, when we talked about gas laws, we talked about gases as being ideal because the particles, particle A and particle A prime, are so far apart that the distance between them is virtually infinite. And that's how we get our empirical gas laws. Now, when we're starting to talk about solutions, and that solutions have a solvent, which is generally water, which is generally liquid, we need to move from the gas phase to a liquid phase, which means that our particles are going to be much closer together. And when we move our particles much closer together, we need to start looking at the interactions between these two particles more closely. Okay? So I'm going to take these away and I'm going to redraw it. A and A prime. They're very, very close. And so there's going to be interactions between the two of them, and they have to stay interacted. Otherwise, our liquid, okay, our liquid where our particles are close, just separates into a gas. And we want our liquids to remain liquids. We don't want to take our water and have it, shazam, turn into water vapor, right? We wouldn't live very long on this planet if that were the case. So in order to look at interactions, we have to go back to this idea of polarity. Polarity is separation of charge in a covalent bond. Okay, covalent bond, remember, is sharing of electrons. Sharing, not transfer. And so how is polarity determined? Well, we determine it via differences in electronegativity. Okay, so everybody should have an electronegativity chart. Either one that I handed out, or one that you get off of Google, or one that's on Blackboard, or an electronegativity chart. Okay, so if you recall, what you need to do is you look at your bond, for example, hydrogen-hydrogen bond, and you assign an electronegativity value. Okay, so this one's 2.1, this one's 2.1, you subtract them. The difference, triangle is difference, 2.1 minus 2.1 is 0. There's no difference between that hydrogen and that hydrogen's ability to attract electrons. However, when we put hydrogen with chlorine, hydrogen gets a 2.1, chlorine gets a 3.0. The difference here, remember, is the absolute value, 2.1 minus 3.0, or backwards, either way you look at it, is 0.9. Remember, our magic number is 0.4. Greater than 0.4, we're going to call that polar. Less than or equal to 0.4, we're going to call that nonpolar. Okay? When you get really high, then you start to say that's ionic-like, but for our purposes, this is our magic number. Okay? So since the chlorine has the higher number, it gets the partial negative. The electrons are pulled towards the chlorine. Okay? If you don't remember that, go back to Unit 2, I believe, in which we talked about polarity. Okay? Now, if we look at water, liquid water vapor, okay, so water vapor, there's one water molecule, there's another water molecule. And remember why it is bent. Okay, it's bent because of VSEPR, valence shell electron pair repulsion. If you don't remember that, you need to go back to Unit 2 where we talk about that. Okay? On the other hand, when we take these two water molecules, Okay, so right now they're water vapor because the distance between the neighbors, is basically infinite. So that water is going to leave that water alone. Now I'm going to take these two waters and I'm going to bring them next to each other. Okay? All right, that's my cell phone and I'm ignoring it. I'm bringing them more closely together, and I have to ask myself, will there be some attractions between these two neighbors? And it has to do with polarity. Oxygen-hydrogen bond, oxygen 3.5, hydrogen 2.1, the difference is 1.4. That's really polar. And that is something you really should commit to memory. Oxygen, hydrogen is polar. Partial negative, partial positive, partial positive. Same thing here. Partial negative, partial positive, partial positive. Now we know that when pluses and minuses come in the same vicinity, they are going to attract. So I'm going to get an attraction here between neighbors, and I'm going to get an attraction here between neighbors. And so what that means is that with these two water molecules, they're going to attract and they're going to stick together. If they stick together, they are going to remain in liquid form. So I could even take my little water molecules here, okay, stick them together, okay, right? They're sticking together, and that's because of the polarity. All right? You have to get them to stick together or they're not going to remain as a liquid. Okay? Now, there are different ways that molecules can attract, but there's a specific one that we want to talk about in this class, and that is called a hydrogen bond. And the hydrogen bond is not really a bond, it's an attraction between a partial positive hydrogen and a partial negative neighbor. So in order to figure out whether something's going to hydrogen bond or not, you have to figure out polarity, and then you have to figure out if there's an attraction. Okay? So some examples. You have to be able to draw a Lewis structure. Okay? So that's why we learned how to do Lewis structures. Okay, now our rules here is carbon is royal. Okay, hydrogen, 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 1, 2, 3, 1, 2, 3, 1, 2. The oxygen's going to be bent because of the lone pairs. Okay? Partial negative, partial positive. So I'm going to create another one of these, and I'm going to bring it within the vicinity, and I'm going to orient it backwards for my purpose. I guess somebody really wants to talk to me. Okay, but I'm ignoring it. Okay, I'm ignoring it. Partial negative, partial positive. So you can see here that I can have a hydrogen bond here. That's an attraction between a partial positive hydrogen, partial negative neighbor. I can have a hydrogen bond here. And notice that I'm drawing it as a dashed line because it's not a bond-bond, it's an attraction. The next segment will pick up on these, and I'll see who's trying to call me.